This is NoteBookLearnings. Every video on this channel is one complete project. Deep explanations, real code, and a fully runnable notebook you can download. Today we are building a text-to-SQL bot. You type a question in plain English. The bot writes the SQL, runs it, and hands you the result table. By the end you will understand every layer of how that works. And you will have the complete notebook, free, link in the description. Let us get into it. Imagine you have a database full of sales data. Your manager asks, which products had the highest returns last quarter? You know the answer is in there. But writing the SQL to get it takes time you do not have. By the end of this video, you will have a Python bot that takes that question, writes the SQL automatically, runs it, and returns the result table. No SQL knowledge needed to use it. And the complete notebook is free, link in the description. Here is the problem most data tools skip. They give you a query builder or a dashboard. But you still need to know the table names, the column names, the joins. A junior analyst stares at the schema for 20 minutes before writing a single line. That gap, between the question and the SQL, is exactly what we close. We close it. Right now. In one notebook. The bot reads your database schema automatically. It uses that schema to write correct, grounded SQL, no hallucinated column names. Then it runs the query and returns a clean result table. Everything here is real running code. Open the notebook, follow along, run every cell yourself. That is how this channel works. Let us get into it. Before we write a single line of code, let us understand what we are building. Because the naive approach, just asking an LLM to write SQL, does not work reliably. And knowing why it fails tells us exactly how to fix it. The naive approach, send the user question to the LLM, ask for SQL, run it. The problem, the LLM does not know your database. It does not know your table names, your column names, your data types. So it guesses. And a guessed column name in SQL is a runtime error. The fix is schema injection. Before we ask for SQL, we extract the full schema from the database. Table names, column names, types, relationships, everything. We inject that schema into the prompt alongside the user question. Now the LLM is not guessing. It is writing SQL against a schema it can actually see. That single change is what makes this reliable enough to use in production. Let us get the environment ready. This project is lighter than the PDF chatbot. No vector database. No embedding model. No Hugging Face downloads. SQLite is built into Python, zero installation for the database. The only packages we need are LangChain for the pipeline and your LLM provider. For the LLM, 3 options as always. Claude is the default, best at writing correct SQL from natural language. Groq is completely free and surprisingly capable for SQL generation. OpenAI is the familiar choice if you already have a key. One flag in the config cell switches between them. Hit run once and move on. Notice how much shorter this install is compared to the PDF chatbot. No FSS. No sentence transformers. No PDF plumber. That is because text-to-SQL works differently, it does not need vector search at all. The schema itself is small enough to fit directly in the prompt. That simplicity is one of the reasons this pattern is so practical. Now the imports. 2 things worth noting here. First, we import SQLite 3 directly. No LangChain wrapper for the database. We want full control over query execution and error handling. Second, we import pandas just for displaying results cleanly. The actual query runs in SQLite 3. Pandas just makes the output readable. Everything else is standard LangChain pipeline components. 3 providers, 1 flag. Claude is the default because it is the most reliable at generating syntactically correct SQL. SQL generation is an area where model quality makes a visible difference. A weaker model produces SQL that looks right but fails at runtime. Claude gets the joins, the aggregations, and the where clauses right on the first attempt. If you want zero cost, flip to Groq. Same code either way, just change the string. Before we build anything, let me show you what this produces. We are going to ask 4 questions against a sample retail database. A simple factual question. A multi-table join. A ranking question. And 1 question that has nothing to do with the database. Watch what happens on the last one. The database and the bot are set up in the cells below. Run this after working through the full notebook, or just watch the output here first. Now that you have seen where we are going, let us build every piece from scratch. We start with the database. Every text-to-SQL tutorial uses a toy database, 2 tables, 5 rows. That is fine for learning SQL but useless for testing a real bot. Real queries involve joins across multiple tables, aggregations, date filters. We need a database complex enough to generate interesting questions. We are building a retail database, customers, products, and orders. 3 tables. Real relationships. 100 rows of realistic data. This is the schema our bot will need to understand and query correctly. We create the database with SQLite 3, no installation, built into Python. 3 tables with real foreign key relationships. Then, we seed it with 100 realistic orders across different customers and products. Notice the variety in the data, multiple cities, product categories, and date ranges. That variety is intentional. It means we can ask interesting questions. Things like, which city generates the most revenue, or which category sells best in Q1. A bot that only works on identical rows is not useful. We have the database. Now comes the step that makes this whole approach reliable. We need to extract the schema and inject it into the LLM prompt. We extract it programmatically, not hard-coded. The bot reads the live structure every time it runs. Schema changes in the database automatically appear in the prompt. No manual updates. It just works. We also include sample rows alongside column names. Sample rows show the LLM what the data actually looks like. Are cities stored as full names or codes? Are dates ISO format? 3 rows answer those questions immediately. This function does the heavy lifting of schema extraction. It uses SQLite 3 PRAGMA commands. These are special SQLite instructions that return metadata about the database structure rather than actual data. PRAGMA table info gives us column names and types. Then, we fetch 3 sample rows from each table. The result is a clean human-readable string that we will drop directly into the prompt. Notice we handle the case where a table is empty, no crash, just a note saying no rows yet. We have the schema. Now, we need a prompt that uses it effectively. This is where most tutorials make a critical mistake. They ask the LLM to just write SQL without any constraints. The LLM writes SQL, but it also adds explanations, markdown formatting, code fences. Then the execution step breaks because you cannot run a code fence in SQLite 3. Our prompt is designed to prevent exactly that. 3 explicit rules. Only use tables and columns that exist in the schema. Return only the SQL query, no explanation, no markdown, no backticks. If the question cannot be answered from the database, say so clearly. That third rule is the anti-hallucination clause for SQL. Without it, the LLM invents tables that do not exist. With it, out-of-scope questions get an honest response instead of a broken query. Now, we build the prompt and the chain. The prompt has 2 variables, schema and question. The schema is always the live extracted schema from the database. The question comes from the user. Notice the not SQL prefix instruction. That gives us a clean programmatic signal when the question is out of scope. We can check if the LLM output starts with not SQL and handle it cleanly. No try except around broken SQL. No runtime errors. Just a clear branch. The chain uses LCEL, the modern LangChain pattern. Schema and question feed into the prompt feeds into the LLM, output is parsed to string. We have a chain that generates SQL. Now, we need something that runs it safely. This is the step where a lot of implementations cut corners, and pay for it later. Running arbitrary LLM-generated SQL against a database is a security risk. If you ever expose this to real users. We add 2 safety layers. First, we only allow select statements. No insert, update, delete, or drop. The bot can read your data. It cannot modify or destroy it. Second, we catch execution errors cleanly and return them as messages. Not as exceptions that crash the notebook. As structured output the caller can handle. The result comes back as a pandas data frame. That gives us clean tabular display, easy filtering, and export options. 1 function. Safe execution. Structured output. The executor function. Clean and defensive. First check, is this a select? If not, we refuse and explain why. Second, run the query inside a try except. If SQLite 3 raises an error, we catch it and return it as a string. The caller never sees an exception, they see a structured dict with an error key. That pattern makes error handling predictable throughout the rest of the code. Notice we use pandas red SQL query to get the result. It automatically maps column names and data types from the cursor. We get a proper data frame back, not a list of tuples. We have all the pieces. Now, we connect them. The ask function is the single public interface, 1 question in, 1 result out. 3 things happen inside. First, the chain generates SQL from the question and the live schema. Second, we check for the not SQL prefix. Out-of-scope question. Return the reason directly. No wasted query. Third, valid SQL gets executed and returns a data frame. The not SQL check is just a starts with call. No regex. No parsing. 1 line separates valid SQL from honest refusals. The ask function. Everything comes together here. We pass both schema and question to the chain. The schema is refreshed on every call, so live schema changes are always reflected. Then, we check the not SQL prefix. If the LLM determined the question is out of scope, we extract its reason and return it. Otherwise we execute the SQL. The result dict carries everything the caller needs, the SQL that ran, the data, the row count. Returning the SQL alongside the data is important. It means the user can see exactly what query ran against their database. Transparency builds trust. For questions. Each tests something different. The first is a simple aggregate, just count. The second requires a join across two tables and a group by. The third needs a join across all three tables, an aggregation, and an order by with limit. The fourth is completely outside the database, watch how the bot handles it. A bot that answers confidently from the wrong source is worse than useless. This one says exactly what it cannot do and why. Everything works as individual functions. Now let us wrap it into a clean class. This is the same pattern we used in the PDF chatbot, and for the same reason. Functions scattered across notebook cells are not something you can import into a project. A class with a clean interface is. The Text-to-SQL class has three methods. The constructor takes the database path and provider flag, sets up everything internally. The ask method takes a plain English question and returns the full result dict. The describe method prints a summary of the database, useful for exploring an unfamiliar schema. Notice that this class works on any SQLite database. You do not hard-code the database name or schema anywhere in the class. Point it at a different database and it reads that schema automatically. That is what makes it reusable. The full Text-to-SQL class. The constructor initializes the LLM based on the provider string. Then builds the prompt and chain. The ask method is exactly what we built before, just wrapped cleanly. The describe method is a bonus utility. It prints the schema in a readable format. Useful when you first point the bot at an unfamiliar database. Before you can ask good questions, you need to know what is in there. The class handles that for you. Let us take the Text-to-SQL class end to end. One line to create it. Then 5 questions, escalating in complexity. The first 2 are single table queries. The third and fourth require joins. The fifth is completely outside the database. Notice how cleanly the class interface reads. No schema visible. No prompt visible. No chain visible. Just bot. Ask and a result dict comes back. This is the interface you would wire to a fast API endpoint. Or a Streamlit text input, no changes needed. Let us take stock of what you actually built here. You understand why schema injection is the key to reliable Text-to-SQL. You can extract a live schema from any SQLite database automatically. You built a schema-aware prompt with an honest refusal mechanism, the not SQL prefix. You have a safe SQL executor that only allows select and never crashes on bad queries. And you have the Text-to-SQL class, point it at any SQLite database and it works. The next project on this channel takes a different angle entirely. We build an ATS resume scorer, paste a job description, paste your resume. And get a score plus a rewritten version of your weak bullet points. The complete notebook for this project is free, link in the description. If this saved you time, star it on GitHub. Subscribe so you do not miss the next one. See you there. The complete notebook is linked in the description. The retail database is created automatically when you run the cells. No files to download. Just run top to bottom. All dependencies in requirements. TXT. Start it on GitHub if it saves you time.